Hi there.
Hello and welcome back to Calculus 1, section 2.5, limits at infinity. So is this different than infinite limits? Sure, because it's a new section. So now, instead of looking for infinity in the answer, we approach infinity. So x goes to positive, negative, infinity, f of x. And on the other end, we are looking for a finite limit L. We will also be looking for infinities, but we'll talk about it when we get there. So there we go. That's what we are looking. So limit at infinity. You go to infinity, and then you look what the answer is. So if I have y equals, let's say, 1 over x, if I draw the function, and I say, what is the limit as x goes to positive infinity of 1 over x? The answer is? The answer is 0. Great. Because as you go to positive infinity, your y approaches 0. It approaches x-axis, so y 0. Another example. Y equal e to the negative x. This is the decay function. So what is the limit as x approaches infinity for e to the negative x?
0.
0, exactly.
0.
It looks the same. All right, next example. You're going to love this one. Inverse tangent of x. So what happens as the limit of inverse tangent goes to, x goes to 0? Now the question is what the graph for that one, right? Well, do we know the values or no?
Just
Pi over 2 and negative pi over 2. Good. So as x goes to infinity, oops, I put 0. I meant infinity. As x goes to infinity, what do we get? Pi over 2. Limit as x goes to negative infinity of inverse tangent is? Negative pi over 2. Great. So this is what we have for our limits at infinity. You go all the way to infinity, and then you look at the y value. Is the y value going to 0? Is it going to pi over 2? So you look at that, and that's the answer for it. So now, what do all of these functions have at these limits? They have which ones? Horizontal asymptotes. So limit at infinity will give us horizontal asymptote.
so horizontal asymptote. I would imagine it's a bit of an inverse for a vertical asymptote.
It's not an inverse. It's just
Well, I meant
it's its own.
Say is horizontal asymptote can't equal infinity.
No, we'll talk. They can equal infinity, but they have a feature that the vertical asymptotes don't have. So, what is the horizontal asymptote? Known as ha. Ha. I don't need the dots. Just ha. So, horizontal asymptote is a horizontal line at y equals capital L, where limit x approaches plus or minus infinity of f of x equals that L. So horizontal asymptote is the function, is a linear line, right? It's a horizontal line at y equals L. So y equals 3 is a horizontal line, y equals 10 is a horizontal line, so y equals L, right? And that L is the limit that we get from our calculation.
Oh, so it does contact the value here.
Well, no, that's the horizontal asymptote is the line, and then the function approaches it. Now, one important thing that to know immediately is that horizontal asymptote can be crossed locally. Horizontal asymptotes must be obeyed only at infinities. So you are going to find functions that pierce through horizontal asymptote, and there are functions that just follow them. You will never find a function piercing through vertical asymptote. So when you so horizontal asymptotes can be crossed locally, but never at positive or negative infinities. So function must obey. Function must obey. So you guys could have a situation like this. We are going to have a situation like this, where you have, I'll put also two vertical asymptotes here. So this is what you have. You have a piece of a function that pierces through, and then two that are following. And you do have a horizontal asymptote along y equals 0, for instance. So that's an example. So as you can see in the middle, for the middle part of the function pierced through the asymptote. Horizontal asymptotes can be crossed because they only bend the functions at infinities. How many times can you cross the horizontal asymptote? Many times. Many times. They are only obeyed at these ends, right? At the infinities. That's the only place where they have to be obeyed. The rest you can. Now, vertical asymptotes are obeyed all the time. Function never touches, never crosses the vertical asymptote. Horizontal asymptotes not as strong. Now, we have seen already examples of all of these, right? All of these examples are your horizontal asymptote. First example, horizontal asymptote at 0. Second example, horizontal asymptote at 0 as well. Third example, horizontal asymptotes at negative pi over 2 and positive pi over 2. Those are also known as bounds. Application for these asymptotes. One of the interesting examples that we can look at is the logistic model for, let's say, population. You have the simple ones that are bad, examples of population. So if you have population is equal to initial population e to the kt, population model, this is terrible because it says that if you wait infinite time, you get infinite population. Well, planet is a finite size, so you can't have infinite population of anything. So it's not a good model. Logistic model is much better. Logistic model is introducing what we call There we go. Carrying capacity of the planet. So you have your initial population P0, just like you had initial population P0 there. Exponential growth, and then it levels off and it follows the carrying capacity K. That translates into, let's say, the maximum amount of humans you can have on a planet. You can support on a planet, because the planet is a finite size, which means finite resources, minerals that you can mine for, finite amount of food that you can grow, finite surface area to build a housing, finite amount of fresh water to drink. So planet is finite, therefore you can only have a finite population. Now, depending on how much we consume, you can have more or less people, which is why scientists can't figure out whether we are capping at 10 billion or at 15 billion, right? We are already at 7.5, so we're doomed either way, right? Whatever the number is. But the thing is that the carrying capacity in this particular example here is the horizontal asymptote that, as you wait in time, you are reaching maximum population. Another example with the same outcome would be spread of the disease, infectious disease. In the past, there was a black plague which killed 2/3 of population of planet. 2/3, right? That means that if you look around you, for every three of you, 2 are dead, 1 survives, right? So this side of the room has 9 students, 3 are going to live and 6 are gone. That's how bad the plague was. Did it kill everyone? No, right? So the infectious disease of any kind, polio was crippling disease. While it's eradicated in almost everywhere, just another 3 to 5 countries left with polio. You are all vaccinated for polio. Not everyone gets sick. Not everyone gets sick, not everyone dies of certain disease. So that's why we still have people around. Otherwise, if the Black Plague was, okay, kills everyone, well, there will be no people, right, for us to have a calculus class today. So there is this carrying capacity for everything, and that would be the maximum amount of people that can get sick, the maximum population that the planet can carry, the maximum population of rabbits that you can have until there is no more vegetation. I don't care whatever, whatever concept you're talking about, but it is today's lecture. You take the limit. Now, this is going to play a big role in differential equations if you take that class, to take the limit as your time or x goes to infinity, to check for validity of your model. Which is why I said the model up there, the first one, is bad, because you cannot have infinite anything on the planet, that it's of the finite size. And since it's exponential growth, another planet really doesn't help. Exponential growth is not linear growth, so extra planets don't help. So now that we understand that limits at infinity are giving us horizontal asymptotes, and we can calculate the limit of the function to get this, we just want to take a look at few examples for the limits at infinity and see some calculation tricks that are given to us to compute these things. So first example, or maybe I should, I'll go with that concept later. So first example would be, say, well, let's first go with the limit x goes to infinity of 1 over x squared, well, first off, this looks like 1 divided by infinity, right? Do we all see that as 1 divided by infinity?
No.
When you plug in infinity, infinity squared is still infinity.
Oh, that's good. Okay.
So what happens if you try to divide 1 infinitely many times? What do you think?
Would you stay one? It will never become 0.
It becomes 0. Very good. So, what?
Go ahead. Go ahead.
We're good? All right. So, behold 1. Right here. This is 1. If I divide 1 by 2, which is a half, right? I divide 1 by 2, this is what I get.
Still 1.
Yeah.
No, it's a half now, right? Now, if I divide by 4, if I divide the original 1 by 4, the result is this, which is a quarter. If I divide the original 1 that I had by 8, it is this much. If I divide by 16, is this much. If I divide by 32, it's this much. There are 32 of these in the original paper. If I divide by 64, it's that. So now, you see that the end result is getting smaller as you keep dividing by larger numbers. This is 1 over 64 is this small in comparison to the original number 1 that you had that was only divided by 1 to give you, right, this. So 1 divided by 1 is this much, and 1 divided by 64 was that tiny little piece. So clearly that as this number here goes from 1 to 2 to 4, I mean, it doesn't have to go 1, 2, 4. It can go 1, 2, 3, 4, 5, 6, 7, all the way to infinity. The actual answer of what you're getting is getting down to 0. So that's a good argument to know. And you can immediately answer a question like this: 1 divided by x squared is equal to 0. Now, clearly you can draw the graph and see, because by now you know this x squared graph very well because we used it a number of times already. And you see that as your x goes to infinity, the y value of the line over here goes to 0. So it's 0. Maybe I should, I'm going to circle it.
Oh, you mean as a slime moves, it moves
As you go,
infinity.
yeah, as you go to infinity, right? As you go to infinity, the black line of the function approaches the x-axis, going to 0. That's your horizontal asymptote. Now, you learned horizontal asymptotes in your algebra or pre-calculus course, and you apply that to rational functions, and probably you don't remember those rules, but there were 3 rules that told you where the asymptote is. Can anyone remember those rules?
No, I don't.
Yeah, you can? All right.
Is it like if the denominator is bigger than the numerator, it's 0?
Exponent of the leading exponent.
So the degree.
The degree, yes.
And then if the degree of the denominator is more, there is no horizontal aspect.
Nice.
And it's, the degree is equal, just about the ratio of the leading coefficients.
Excellent. You remember all 3 rules. Great. Now you have my permission to forget them. So we are going to now learn the method, so you don't have to remember that anymore, right? You can retire it. So great. That's exactly correct. In pre-calculus, we take a look at the function where you had the polynomial divided by another polynomial, and then you take a look at their front coefficients. Let's say a equals x to the p and b x to the q. And then you had to memorize those three rules. Now they're still going to hold, but we're not only going to deal with polynomials, we're going to deal with calculus concepts. So you can use it or you can forget it, whatever. So if P is larger than Q, no ha. If P is equal to Q, horizontal asymptote at y equals A over B. And if P is smaller than Q, so Q larger on the bottom, ha is at 0. So this is what you learned in your pre-calculus course. And obviously requires memorization and annoyance and all of that stuff. Now, if I give you a question, limit x goes to infinity of x cubed plus 6x minus 9 divided by x squared plus, x to the fourth plus, let's say 10, then if you know the rules up there, if you memorize the rules from before, you just look at the rules and say, oh, okay, the highest exponent in the denominator, therefore, asymptote at 0. Great, right, you're done. But in calculus, we learned now this limit, and if we solve this limit, we will get 0. So how do we solve the limit? Well, when you have polynomial, now this trick is only for polynomials. It doesn't work if you have trig or exponential logarithmic. So it's just polynomial, divided by polynomial. You pick so somewhere in a problem is going to be a term with the highest exponent. And in this case, that's x to the fourth. So you divide by highest exponent everywhere. Now, note that the limit, as we discussed earlier when I was folding that piece of paper, note that limit goes to infinity of any number divided by x to any exponent is 0. This falls into the category, you better know this or else, right?
All right. Give me a moment.
So any number on top, this can be 70 million, it doesn't matter. Any number divided by x to any exponent. It could be x to the first exponent, it could be x to the 10th exponent, it doesn't matter. It has to be positive. I have to specify n larger than 0. So use the algebra, and all of these will cancel. You have 1 over x plus 6 over x cubed minus 9 over x to the fourth, 1 plus 10 to the x to the fourth. And look at this. Every single one of these, other than 1, goes to 0. The first one goes to 0, next one goes to 0. All of these go to 0 because that. Then you are left with 0 divided by 1, which is 0. Yes?
So they go to 0 because we're plugging in infinity.
1 divided by infinity, it's gone, right? 9 divided by infinity, well, you just take 9 pieces of paper, they're still gone, right? So anything that you cut infinitely many, right? Cutting, guys, right? Cutting makes smaller pieces, right? You take a piece of bread, you cut into 2 pieces, right? So, and then each piece is smaller than the original piece. So as you cut, if you cut infinitely many times, it goes to 0.
So how so are you saying that the max, the highest, that exponential value is going to be equal to 0?
No. I said that you divide by the highest so that you can cancel, and you cancel them all to use the rule here. Yeah, to simplify.
By this being approximately 0?
No, it's exactly 0. It's not approximately 0. It's gone because you're dividing by infinity. Yeah.
What way?
Just by division. That's what this means here. Think about it. What do you have?
Oh, sorry, I actually forgot about the rule next to my. I forgot
You okay? So until I pointed the arrow.
Yeah,
That's because I read minds.
yeah, thank you.
Yeah. Stop thinking that. All right.
So for any value, for any variable, it's going to end up being divided by infinity?
Not the variable, value.
Value.
Mm-hmm.
Well, what's these symbols represent the value? N, X, A?
I'm not sure what you're asking, XAA.
That's the important equation there. So,
This is any number, like I have 9 over here. All right, so now, problem 18, by popular demand over here, we're gonna do some trig. 5t squared plus t sine t divided by t squared. Now, one cool thing about trig and these limits that go to infinity is that sine and cosine are bounded by 1. So they don't actually count in these problems at all. Yeah, you can just ignore them. See, sine x is bounded by 1 and cosine x is bounded by 1 because they never go higher than 1 or lower than -1. So the most this can be is 1. It cannot be 1.7, it cannot be 10, it can only be 1, and that's it, at most. It could be 0, it could be anything else, all the way down to -1. So it's bounded, we say just bounded by 1. So because of that, you can just ignore it. It's as, you can replace it by 1. That's the most it can be. Which is why it doesn't contribute to the limit calculation at all. So this problem technically is 5t squared plus t divided by t squared. Because this sine t doesn't contribute at all to the limit at infinity. And when you divide everywhere by t squared, that's our rule to solve these problems. We get 5 plus 1 over t divided by 1. By the rule, 1 over t goes to 0, and the answer is 5. So this function would have a horizontal asymptote at 5. Horizontal asymptote that will be obeyed by the function at infinity.
That's why t over t squared becomes 1 over t.
You cancel t, right? You were just testing me, right? To see if I know.
Sure.
Exactly. Oh, you can't see this.
I can't.
So 5x squared. Do you see that? We just calculated that the horizontal asymptote for this problem would be y equals 5 because the limit at infinity is 5. Look at the graph. How many times did this function cross that asymptote? Infinitely many times, right?
Yeah.
But if you are to scroll to the right, do you see that it settles at 5? It settles at 5 because that is horizontal asymptote, right? So horizontal asymptotes must be obeyed at ends. They do not have to be obeyed locally, which is why the function is allowed to cross it. But then at infinity, it must follow that line. Yes?
I'm sorry, does locally mean like in a certain point of the graph or just small sections?
Locally means wherever you look at it.
Okay.
Because there's only one place where you can't look. Where is that place? At infinity.
Yeah.
That's the only Chuck Norris can do that. The rest of you mortals, no. Good. Let's do more pre-calculus redefining. What happened? Flashbacks? The pre-calc, yes. Just wow. Yeah, I know. I have the same feelings. It's wonderful. It's wonderful. You remember end behavior of a function? No? Okay, let's review it.
Oh, yeah, of course. That's just which plane, which direction, the range, the.
Yes, which direction function goes to. So end behavior. Good one. Draw this in the center because we need to write in the 4 regions. Yeah, so we can have the end behavior going this way, that way, that way, that way. See, if you combine these two, you can get x squared. If you combine these two, you get negative x cubed or tangent. So, oh, not tangent, sorry. Negative x cubed, tangent has asymptotes. If you just look at this end, going this way, you get your exponential function. So, end behavior. Note that for this particular arrow in the first quadrant, as your x goes to positive infinity, your y goes to positive infinity. You all seen vectors at some point in life, and you know to decompose the vectors, right? So if there is a vector at an angle, it has the two components, x and y component. So the x component would be moving towards positive infinity in the first quadrant, and the y component goes to positive infinity as well. So for the first quadrant, the end behavior is described as the limit x goes to positive infinity of f of x and gives us positive infinity as the answer. It doesn't give us finite L because it will be horizontal asymptote. It gives us positive infinity. So that's called the end behavior. The one on the bottom, limit x still goes to positive infinity because the arrow moves towards the right. But the answer that we get is negative infinity this time because arrow is pushing downwards forever. And then on the left side, the upper one is limit x goes to negative infinity now because it goes towards negative to give us positive infinity as the answer. And finally, limit x goes to negative infinity here of f of x is equal to negative infinity down there. So in a pre-calculus book, you only had what I drew in black. Calculus is now adding the definitions of those in red. So when you take the limit and you get infinity, then that means that there is no horizontal asymptote and the end behavior of the function goes either up forever or down forever, depending whether you got positive or negative infinity. Now, to take a look at complete problem, we just say y equals, let's say, e to the x. So when you draw e to the x, function, here on the red side, we have limit x goes to negative infinity of e to the x, and that's 0. So that's the horizontal asymptote at y equals 0.
Oh, yes, the first one's 0.
Yes, as you go to the left, to the negative infinity. Now, on the other side, the blue one, you have limit x approaches positive infinity of f of x, and that gives you positive infinity. That's end behavior. So no horizontal asymptote there because you did not get the finite number, and the positive infinity there gives you the end behavior, not the horizontal asymptote. So you can, right, they can, right, mix and match. Your inverse tangent had two asymptotes as you go to negative infinity, positive infinity. Two different asymptotes. Some problems will actually have the same asymptote because eventually we're going to run into something that looks like this. So it does something like that, let's say, right? That's asymptotes on both ends.
Oh, yeah.
So you can do that. So there are many configurations. What you are supposed to learn, guys, is, again, learn the theory. Don't learn example by example because I'm going to switch this with the square root. I'm going to switch this with the ln. I'm going to switch this with, right? And as soon as I switch this, if you just learned one example, then you have no clue what's going on. Learn what the notation means. X goes to negative infinity. That means x goes to negative infinity. What is happening with y's? Y's are going down towards y equals 0, which is the answer. On this side, as x goes to positive infinity forever, the y goes to positive infinity up there. So positive infinity for x, positive infinity for y. Negative infinity for x in red, 0 for y because it's approaching the axis. So those are that's the end behavior. And I don't know why, but they give you all the end behavior for e to the x, e to the negative x, ln x. But that's that. All right. So let's take a look at now. I did say earlier, I'm just going to put this over here as a warning. Limit x goes to infinity for sine x does not exist. So be very careful about that. Earlier, we did have whatever, sine or cosine, whatever was featured, the same. And I said, it's bounded by 1. Yeah, but the previous problem was divided by x or x squared or whatever. So in that case, you can use that rule.
Divided by t squared.
But t squared, okay, so that will be equivalent to x squared here. But now you have only sine x. Sine oscillates like this. And because it oscillates, and infinity is not a finite location that you can look at the sine, at infinity, all of these values from -1 to +1 are all jumbled in 1, which is not a cohesive number, obviously. So you don't get to claim the sine or cosine to have limit at infinity. So limit does not exist for sine or cosine. Now, in this case here, sine was the part of the larger problem, and you see that when you have a sine here, the most it can contribute, because it will be divided by t squared later, right? There is a division in t squared. So I can replace sine by 1 because sine is divided by something. And that something actually grows, right? The t squared grows as you move away from the 0. And sine t never grows past 1, which is the reason why we are able to replace it. So that rule might be a little bit confusing. I did show you the graph to see that what we had earlier is correct. So just be careful when the trig ones come up. If they are alone, sine and cosine, then the limit doesn't exist. If they are part of the bigger problem and they're divided by a value, then most likely you will be replacing them by 1 and then just go from there. Good. So one more problem, and then apparently we have to go.
I agree. I think you did good enough today.
So 32, it says limit x goes to infinity, right? One of our limits. Lock the doors. 6x squared, 4x squared plus the square root of 16x to the 4th plus x squared.
I used to. I did it.
Yeah, but like. That's what I'm saying. That's what I thought. That's what I thought. Because if you're first, then I know what you're saying. That's the scary thing. Because you're busy. That's what I'm saying. That'd be long. I know. That's what I started doing too. Because then I think if we take that right, I think we put the same thing. Which was second. X squared times. X squared times 16. X squared plus 4x plus 4 x plus 1. This is what I asked for. I should probably show that. That's what I was saying.
So what is the highest exponent that we get to divide by?
4x cubed.
What? What?
4x cubed. Where did you get 4x cubed from? Which exponent are we dividing by? X squared. Good.
What?
Yeah, that's all the square root. That's the first step.
So,
Yes, that's what I did.
so when you divide by x squared everywhere, when this x squared undergoes the square root, it will become x to the fourth and cancel it. Great. When you stuff a variable in the square root, it picks up a power. So we had 6, 4 plus, and now the square root of 16x to the 4 divided by x to the 4 plus x squared divided by x to the 4 when you stuff x squared inside. And now when you simplify those, we get 6, 4 plus square root of 16 plus 1 over x squared. Now in the limit, 1 over x squared will go to 0. Square root of 16 is, thank you, so this is 6 over 8, which is 3/4. What one? That's it. Homework is open. You can enjoy. Tomorrow we are going to end the chapter. Bye.